In the last chapter, we did hypothesis testing of a sample, and we went through a process of trying to verify whether there was evidence to support the claim or we lacked the evidence to support the claim. We're going to do the same thing in this chapter. The only difference is, instead of looking at one sample and whether or not that gives us information about the population, we're now going to look at two samples. The two samples can potentially come from two populations, and generally speaking, what we're trying to decide is there a significant difference between the two samples, and therefore between the two populations. Otherwise, pretty much everything is the same as what we've done before, with the exception of we'll have different test statistics because now we have to look at two samples instead of one. But otherwise, same process, same steps in general that we did before, just a different equation. And that's what we found in the last chapter. There was a different equation every time we changed what it was we were focused on: proportion, mean, standard deviation, and so forth. Well, now we're going to do the same thing. It's just the equations will change because we're looking at two samples. If you go back to the previous chapter, however, you will see that the test statistics are very, very similar, with the exception of now there's two of the samples instead of just one. So first off, we have what are called independent samples if the sample values from one population are not related or naturally paired with the sample values from the other population. On the other hand, they are considered dependent, and we will look at that later in the chapter, if the values are paired, such as before and after, for the same subject, or each pair of sample values consists of matched pairs, such as husband and wife. The test statistic for two means, and again, independent samples, and we know the standard deviation, so we know sigma 1 and sigma 2 for the two samples, then the samples are large enough, they need to be independent, random. If all that's true, then we can use this equation to determine the test statistic, the z-score, for that situation. So again, if you go back to the previous chapter, you'll see how similar that z-score looked. Basically, it was x1, the mean of the sample, subtract the mean of the population over the square root of sigma 1 over that. Also, please note, these are sigmas, not s, so these are the population standard deviations, not sample standard deviations. So let's look at the steps for the traditional method. These are the same steps that we've done in a number of sections. First, what is the symbolic form of the claim? Second, symbolic form for the claim is false or the counterclaim. H1, the alternative hypothesis, is the claim that does not contain the equal sign. H0 is the claim, that's the null hypothesis, that's the claim that does contain the equal sign. We select alpha based on the seriousness of the type 1 error. Generally, they're going to give it to you in the problem. Usually alpha is 0.05, sometimes 0.01. Those are common. We identify the relevant statistic and determine the sampling distribution. For example, in this particular section, we're looking at the mean when we know sigma, the standard deviation of the population. And then we know that we're going to use table 4 to find our z-score. After we find the test statistic, the critical values, the critical region, we draw a graph. It kind of helps us visualize where things are, but the bottom line is we reject the null hypothesis if the test statistic is in the critical region, or we fail to reject the null hypothesis if the test statistic is not. What it comes down to is we're going to have, in this case, two z-scores, one for the test statistic, one for the critical value, which is based off of alpha. If the test statistic is more extreme, further from the mean, then our critical value, it's in the critical region, it's in the rejection zone, and then we can reject the null hypothesis. But if it is closer to the mean, it is inside of our rejection area, then we fail to reject the null hypothesis. And then finally, we restate the result in simple terms and address the original claim. Now, we can also do the confidence interval method, and really all that's changed here is instead of x bar minus e and x bar plus e, we have two samples. And again, what we're really looking for is the difference between the two samples and what that tells us about the difference between the two populations. And then we have our margin of error equation, a little bit adjustment for the fact that we have two samples. So really, almost all of this is just like what we had before, except certain pieces have been altered to take into account we have two samples instead of one. So let's look at an example problem to see how this would play out. So first off, we have a credit card watchdog group claims that there is a difference in the mean credit card debts of people in California and Florida. The results of a random survey of 250 people from each state are shown below. The two samples are independent. Do the results support the claim? So again, the claim is there is a difference in the mean debt of people from California and Florida for credit card debt. Clearly, looking at the two sets of numbers, the means are different. The standard deviations, and note, again, these are sigmas, not S. So this is the standard deviation for the California population. This is the standard deviation for the Florida population. They are different. The real question is, are they different enough that we can support the claim that there is a difference? Or is their difference just a matter of random chance, that every time you do another sample, you're going to get a little bit of difference randomly? So let's go through our steps. First off, the claim is that they're different, do not equal each other. So the counterclaim is they do equal each other. However, the null hypothesis always gets the equal sign. So in this case, the null hypothesis, that's what we're going to test, is that they are the same. And the alternative one is that they're different. Our alpha is 0.05. We're going to use a normal distribution, which means table 4. So, because this is a not equal to, it's a two-tailed test, which means if our alpha is 0.05, then it's 0.025 in each tail, which means our critical value is plus or minus 1.96 for our z-score. Okay, here we calculate our test statistic, the means of each sample. Note this is 0 because since we're saying they're equal, if you subtract each other, then they have to be 0. And then we have the sigmas and n's in the denominator, and we come out with a z-score for our test statistics of 1.854. Now please note, 1.85 is less than 1.96. In other words, this is closer to the mean, closer to the inside of the distribution than this one is, not in the rejection area. Again, the rejection area is always an extreme value. Therefore, we fail to reject the null hypothesis. The null hypothesis was they could be the same. So we can't reject that. They could be the same. Please note, we're not proving they are the same. We're just saying we can't reject the possibility that they are in fact the same thing. And therefore we say there is not sufficient evidence to support the claim there is a mean difference in the debt. So that is the traditional method, or sometimes called the critical value method. Now, what if we want to make it do a confidence interval method instead? Well, again, our alpha is 0.05, so the critical z-score is 1.96. It's got to match what we did up there. But this time we're going to do our margin of error, and so it's the 1.96 times sigma 1 over its n1 and sigma 2 over its n1. Don't forget to square. If you don't square those things, you'll get a false result. So we come out with our margin of error is 158.54. Now, note, this is x1 bar minus x2 bar, so the mean for sample 1, subtract the mean for sample 2, and then subtract the margin of error, and then over here, add the margin of error. So sometimes it's a little bit easier to write it out. Let's just find the difference between the two means. So 3060 subtract the 2910, that gives me the 150. So basically I'm going to have 150 subtract the 158 and 150 plus the 158. And that'll be my confidence interval. So basically it comes out like this. I go from negative 8.54 to positive 308.54. So the process would suggest that the true value of the difference in the means has to fall between there. But since this goes from negative to positive, then that means 0 has to be within the confidence interval. Therefore, we fail to reject the null hypothesis. There is not sufficient evidence to support the claim. You should be getting the same results. Okay, the difference here is we were looking for a z-score that was more extreme. Here we were looking for, does our null hypothesis fall within the confidence interval or not? Now, I didn't mention it on the first page, but you can do the p-value method, of course. And don't forget, the difference between critical value and p-value is the critical value compared the two z-scores. The p-value compares the areas that those z-scores bound. So, two-tailed test like it was before, the test statistic that we did up above gave us the 1.85. That z-score would give us an area of 0.9678 to the left, which means to the right it's 0.0322. Now, since this is a two-tailed test, we have to do 2 times the 0.0322, which gives us 0.0644 for our p-value. That is greater than our alpha. So again, the difference between p-value and critical value is, here we're comparing the two areas. And of course, where did we get the 1.96 up above? We got it from the 0.05. So these are the z-scores, these are the areas. Same result, we fail to reject the null hypothesis. There is not sufficient evidence to support this claim. Let me finish just by saying, if you go back to the previous chapter and you look at just doing a mean where you knew sigma, almost everything is identical to what I just did here, except we have a different z-score test statistic equation, and we have a slightly different margin of error equation, but all the rest of the steps are the same, and how we interpret the results are the same in terms of whether we're going to reject the null hypothesis or fail to reject the null hypothesis. So, that's section 1.